So if Bob says head, and then Alice went, I'm sorry, this is tail, then to prove that, well, she is going to tell the telephone the name, and Bob can check whether she's lying or not, right? So this is a very simple protocol, and there's a computer sciencey version of that using hash functions. But of course there are issues here because, of course, if Bob can find the online version of the telephone directory, he can cheat quickly. Just use a Control F, and then you'll find quickly, right? And so how can you circumvent such problem? And this is where the number theory comes in. So now I'm going to give you a protocol which uses some number theory to solve this problem. So Alice picks two large prime numbers, P and Q. For technical reason, they have to be of the form 4n plus 3. That means when you divide the prime by 4, it leaves the remainder of 3. What she does, she picks two large prime numbers, multiplies them, which is an easy operation, sends the product over to Bob. She keeps the primes P and Q to herself. That's secret. What does Bob do then? He picks another integer s, which is less than n, relatively prime to n. He squares that number, reduces it mod n, gets the number a. And he sends a to Alice. Alice then solves a quadratic equation, x squared congruent to a mod n. And this I'll explain in the next slide. This will have 4 solutions, s minus s and t minus t. Now Alice has to guess what pair Bob has. Well, Bob has s, because that's how we constructed this equation. If he has s, he also has minuses, right? So if Alice picks the pair that Bob has, then she gets the car. Otherwise, Bob's will get the car. And to prove that he won, he will reveal s. Okay, so if you're seeing this protocol for the first time, it might look confusing. So I'm going to explain with an example, and then I'm going to open it up further. So let's take the primes 3 and 7 and multiply them, get 21, and then Alice sends 21 over. Of course, this is a very naive example. In practice, you'll be working with primes which are 100 digits long, but just to illustrate the idea. So you get 21. Alice picks a number less than 21, which is co-prime. Let's say she picks 10. She squares it, gets 100, and divide by 21. 21 goes 4 times. That gives you 84, and the residue is 16. Right? Sends 16 to Alice. Then she solves this quadratic equation, and she gets these pairs. Well, 4 squared is 16, so 21 minus 4. Well, this is really, 17 is really minus 4 mod 21, and 11 is minus 10 mod 21. So 10 minus 10, 4 minus 4. Right? Now she has to send one pair over to Bob. If she sends 10 comma minus 10, then she wins because she's guessing the pair correctly. That was the one Bob has. But if she sends the wrong pair, then she loses. That's the protocol. So in more details, the first 2 steps are straightforward, right? Multiplying, sending it over, finding a number less than that which is co-prime, squaring it, reducing. So elementary operations, Euclidean algorithm, there's no problem there. The real interesting bit is in solving the quadratic equation x squared equals a in Zn or mod n, right? So here's where just a tiny bit of mathematics comes in. So this is at least one solution, right? Because that's how it was constructed. A was obtained by squaring something, namely s. So you know that this is a solvable equation. It has one solution, s, and therefore it also has minus s. Now, the Chinese remainder theorem, if you have taken Math 236, you have probably seen some variant of this one. Because P and Q are distinct primes, the classes mod n break as a product of the classes mod P times the classes mod Q. So this equation now breaks up into 2 equations, 1 over P, 1 over Q. And working over P, you get 2 solutions from here, 2 solutions from here, combine them, that gives you 4 solutions. Okay? That's how you get the 4 solutions. Now, how do I solve this one? This is Chinese humor. How do we solve a quadratic equation? Well, you know the quadratic formula for solving a quadratic equation over the reals, right? You can also do it over integers. And here is the answer. If you want to find an integer x whose square is a, that is, you want to find the square root of a, there is a closed formula for the square root of a. And this is the reason I need the fact that p is congruent to 3 mod 4 so that p plus 1 over 4 is an integer. So, and you can check, you can plug in, you can raise it and do modular arithmetic, you can get back a. So that's the formula. So here's an example. Suppose x squared equals 2 mod 7. You want to find an integer x whose square is 2. Well, 7 is a small number, you can check one at a time. But if the prime is astronomically big, there is no way you can check everything by hand. You need a closed formula. And the answer is plus or minus 2 to the 7 plus 1 over 4. 7 plus 1 over 4 is 2. 2 squared is 4. And you can check when you take 4 and you square, you get 16. And you divide 16 by 7, the residue class is 2 because it goes 14, right? That is to say, the square root of 2 is plus or minus 4 in the world of integers mod 7. Okay, so that's how it goes. But the punchline is in the last step because recall that Alice sends Bob one of the pairs, S minus S, T minus T, one of the pairs, right? She will win if and only if she sends the correct pair. And a priori, she doesn't know which one Bob has, right? So let's consider two possibilities. Alice sends S comma minus S. Then that's the right pair. But Bob cannot claim that he has the other pair. Because Alice is not stupid. She's going to say, okay, tell me what pair is it, right? And he has to reveal that. And he doesn't know how to solve the quadratic equation because he doesn't know how to factor n. So it all relies on the impossibility of the factoring n, right? So Alice wins in this case. Now, Alice sends t comma minus t. Well, this is a much clearer case because Bob will win because he will instantly declare, oh yeah, here's the other one that I have. Right? So bottom line is that this is a cheat proof algorithm. There's no room for cheating here, right? But the key point is there is no known fast algorithm to compute the roots of a quadratic equation mod n without knowing the factorization of r. It really comes down to this fact. As of today, we don't know how to do that, right? So the only way to hack the break the protocol is to either find a fast algorithm for factoring n as a product of PQ or solving the quadratic equation. That's the only way to go. And it turns out that both these problems are equally hard on the time complexity scale. Yes?
So is that NP complete?
I'll get to that in the next slide. Yes. So you have two problems. Find the prime factorization of n or solve the quadratic equation. And I claim that these two are equivalent. And here's a simple proof. Well, solution to 1 implies solution to 2. That's very straightforward. I already told you. If you know how to factor n, Chinese remainder theorem breaks up into two equations. And I gave you a closed formula for solving each. So 1 implies 2 is very easy. What about 2 implies 1? If I know how to solve the quadratic equation, how is that giving me a factorization of n? And if you know the roots of the quadratic is s and t, then here is the factorization of n. I don't have time to prove, so I say it's a soft exercise in elementary number theory, which I will leave it here, right? And both these problems belong to the class of NP. It is not known whether they are NP complete or not, right? So what is NP? These are problems which hard in the following precise, following technical sense. Given a solution, it is easy to verify whether that's the right solution or not, but it's hard to find that solution, right? In contrast with P, which is problems which have which can be solved quickly in polynomial time. And it is believed that these two classes are different, and that is the famous Millennium Prize problem. Okay? So now you can ask, okay, there are all these super fast computers. Why can't Bob use a computer to factor n, right? And when I say it's a hard problem, sometimes it doesn't really sink in our brains. What do we mean by hard? Just to give you some numbers, this is nearly impossible, and the complexity, the arithmetic complexity is enormous. A single 2.2 gigahertz machine takes about 70 years to decompose an integer n with 200 digits into its prime factors. Right, just one machine, right? But you can do parallel computing, and so let's a cluster, a large assembly of IBM supercomputers cut down the computing time to 1 year, right? So just one integer n, which has 200 digits, right? We're talking about 1. And if it is predicted that factoring a 200-digit number in 1 year would take 200,000 Pentium class machines, right? Just some numbers to so that you can get a feel for the magnitude of the time complexity here. So this is the reason why the RSA laboratories started the so-called factoring challenge back in 1991. So this is to encourage research in the field of computational number theory and determine the strength of the RSA protocols, in RSA cryptography in particular, right? And they said, okay, we're going to give you cash prizes for factoring these numbers, which are called semi-primes, numbers n that can be written as product of P2 distinct primes, right? So it is known that these numbers are constructed by multiplying two random prime numbers. Now you have to tell what those prime numbers are, right? And the smallest one was done in a few months. It was 100 decimal digit, and then people were very optimistic. Oh, we are getting somewhere, but then quickly they realized that once you go from 100 to 200, the time doesn't double. You know, it more than exponentiates that, right? So the time complexity is not linear on the bit size of n, and many of the bigger numbers are still not factored, and they're predicted to be unfactored for quite some time. So one interesting result in 2010. There was one number which has 232 digits, and it has been factored, and this was a result of a combined effort of several researchers working together, hundreds of high-powered machines. They kept running for 2 years. So that's the number, RSA 768. It's a famous number, right? So that was the number, and they joined forces using many machines running parallel over 2 years, and the outcome was the integers p and q, right? So P in blue, Q in green. Now notice that this is if I tell you the numbers P, and if I give you the numbers P and Q, it's a piece of cake. Well, piece of cake, of course, using computers, you can multiply the two numbers using any software to get, I think when Wolfram Alpha will do it, you can get that number right. But the hard part is the converse, and that's the beauty and the power of the one-way functions. Easy to go in one way, very, very, very hard, extremely hard to go the other way, right? So it's very hard to get the decomposition of this number as a product of two integers. Okay, so that was the RSA 768. And then RSA announced $200,000 cash prize, currently inactive, I'll tell you why, for factoring the following 617-digit number. So this is RSA 617. So here is the number. It is known by way of construction that this number is obtained by multiplying two prime numbers, right? So you just have to tell what those numbers are. So back when I was a graduate student, about a little more than 10 years ago, it was, I think, active. So there were students who were making fun that, grad school is not getting us anywhere, at least let's get some money by working on this. So, but anyway, people worked hard, but nobody was able to crack this one. It's still open. But now it's not active because the RSA folks, they really become pretty confident that we are at least secure in the near future. So this is a number. There is no cash prize associated to it, but if you can crack this, you will become very famous. Right? In particular, your name will be on Wikipedia. So let's look into the future. So the RSA 617 is predicted to be factored in 2040. Okay, so people who do estimation time series analysis, they kind of predict the speed at which the computer power is growing, and then they come up with these estimates. I'm not sure how accurate these are, but that's the estimation. So all that is with the classical computers, right? Now, the question is, what about quantum computing, right? And I'm not an expert. I don't know anything about quantum computers really, but I'll say it's still very primitive. The research, it's ongoing. It's very primitive, and the only result we have here is the following, which looks a little bit embarrassing. In 2012, the best they could accomplish was the factorization of 21 using the Shor's algorithm. It's a quantum computing algorithm as 7 times 3. So that's the current state of the art, with quantum computing. But we have a long way to go. But it's kind of interesting. The theory is there, but the implementation issues and all that things they have to come over. It's really a problem in engineering more than fundamental science, I think, at this point. At any rate, if RSA comes through, then that is going to surely crack the factorization problem. So the current RSA will break down, but then there is a new cryptography that is going to take its place, which is proved, again, theoretically to be unbreakable. So that's the quantum cryptography. So the moral of the story here is decomposing a large integer into its prime factors is a very, very hard problem. And the central pillar of our infrastructure, the RSA and other protocols, relies on this. The impossibility of factoring these numbers in any reasonable amount of time forms the basis of these protocols, right? And I think that's where things stand right now. So the reason I'm confidently able to swipe my card wherever I go is because I know that primes cannot be decomposed easily. Okay, I think I'm going to stop here.
Are there any questions for Dr. Chebolu? Comment?
So the prime factorization, we don't have a polynomial time algorithm for, but the problem is still NP, it's not NP complete, right?
Yeah, it is NP.
So that means that's, I mean, at least in theory, someone could come up with a
Exactly,
polynomial
and
time
that is what's the scary part, because until 2004, people thought that primes was also
yeah, well,
NP,
NP
right?
complete.
And then suddenly these folks in India, they came up with a polynomial algorithm, and then people were shocked, right? So that is the fear that, some
so
days...
all of encryption is based off of nothing.
Yeah, if you think about it, it's a little bit scary, right?
Yeah.
Yeah, if some guy somewhere comes up with a clever polynomial algorithm, we are doomed,
Right.
Hopefully that's not going to happen, at least not in my lifetime. Yeah, good question. Yes?
You did mention elliptic curve cryptography a little bit.
Yes.
Fascinating. How does that solve the problem that you just illustrated?
Oh yeah, so that is where the discrete log thing comes up. Yeah. So this is a discrete log problem. So you have a group G and a generator G. So it's like a finite group, and let's say G is a generator of this one. So often the group is taken to be the multiplicative group of a finite field, which is known to be cyclic group. So it's generator. So the discrete log problem is that given G to the A, find A. So, well, A is the logarithm of G in quotes, log in quotes, right? So that's a discrete logarithm. So if I tell you the power of G, can you tell me what the A is, right? For some groups, small groups, this is very easy. But for large groups, this is very, very hard. So now you go through some standard classes of groups. And one simple group that we know as number theorists is G equals FP. That's a prime example. The multiplicative group of a finite field. The other one is elliptic curves. Neil Koblitz, his office was just a few offices down my office when I was a grad student at University of Washington. So he proposed using the group of points on an elliptic curve. If you have any cubic equation and you plot the points over a finite field, the set of points, there is an addition law that forms a group. So that's called the elliptic group associated to that curve. And you can use, instead of FP, use EP. So EP is the set of points on the elliptic curve over a finite field of P elements, right? So not this one. Or you can take FP, that gives you all this factorization business type of thing, or you can take EP, the points on an elliptic curve. So if you take any elliptic curve which is like a donut shape, there's a way to add the points. Given any 2 points, the way the addition works is you join them by a line that meets at some point, and then you reflect that point. So this is A, this is B, and then this is A plus B. So that gives you a group, and once you have a group, this is how it works. Basic point is the discrete log problem is very, very hard to solve on some elliptic curves which are suitably chosen. And this is all that I told you here is cryptographic protocols based on the factoring problem. You can design cryptography based on elliptic curve discrete log problem. Yeah, so some of these I think I will definitely include in my course proposal for Math 330 prime. 330 is number theory. I want to send a course proposal for key applications of number theory and cryptography. Yeah, so. And you can read Koblitz books for more details about it. I think it's good. It's going to take over time.
No other questions? Please stick around. We've got refreshments up here, so please help yourself. Feel free